Hey, it's Mr. Shrum, and I am back with a physical science tutorial walkthrough. And this will be the last walkthrough before our winter break. So this is the last assignment that has a suggested deadline by December 17th. So this is why I'm uploading it this week. And this focuses on kinetic and potential energy. And we're going to be solving problems in a different way compared to before, but it's very similar. So let's take a look. So for the introduction into this lesson, we are told that when players set a soccer ball in motion with their feet, legs, or heads, they're demonstrating force in action. When we apply a force to an object, we usually want it to move, stop, or change direction. And in the world of physics and physical science, we're doing work on the object. And in this sciencey way, the ability to do work is called energy. Energy allows us to move, stop, or change direction of any object we come into contact with. So think about the energy in a simple rubber band. In its natural state, it has none, right? If it's in a drawer full of rubber bands, they're not exerting a force. They're just laying there. But if you take a rubber band out and then you stretch it over your finger and you put a pebble, a little rock in it, and then let it go, it will fling the pebble away because of the elastic nature of the rubber band. So within that rubber band, there is a bit of stored energy in that stretched rubber band. And we're going to study what kind of energy that is in this lesson. Another example, a stone resting on a sheet of glass doesn't have energy. But there is some energy in the stone if you raise it above the glass. There's also energy in the stone when you drop it. If this person drops a rock from high enough, that glass will break because it will have enough energy to force on the glass. And one more example would be a parked car can do nothing, but a car in motion can. The parked car has one type of energy and the moving car has another type of energy. In this lesson, we're going to look at each of those examples in detail to learn about the types of energy. The first energy we're going to look at is potential. So this corresponds to the example with the rock. A stone raised above a sheet of glass has some energy because if released, it will fall on the glass and break the glass. Any falling object accelerates toward the ground due to gravitational force. This gravitational force, which acts on an object, depends on the mass of the object. A heavy object will be pulled toward the ground with greater force than a lighter one. The acceleration of an object while falling due to gravity is denoted by G. The force of gravity does work on the object by pulling it toward the ground. So force does work and energy is the capacity to do work. Because of its position over the glass, the raised stone has the potential to break the glass. Energy that an object has due to its position is potential energy. And let's look at that in more detail. Potential energy is energy stored in a body or an object that can be used for doing work later. Another example, a wrecking ball demolishes buildings. Before striking the wall, someone pulls it back and releases it to hit the wall. The farther you pull the wrecking ball back, the more impact it has on the wall. The position of the wrecking ball determines how much potential energy the ball actually has. A bow and arrow is similar. The more you pull the bowstring, the farther the arrow is likely to go. The position of the bowstring has an impact on the distance covered by the arrow. In other words, the position of the bowstring determines how much potential energy the bowstring has. Potential, think of the potential to use that energy later. It's storing the energy to be used at another time. Potential, position, think of the PO in potential and the PO of position being connected. The potential energy of the wrecking ball or the arrow, the bowstring, isn't due to gravity alone, because these objects are not free falling. Any type of force can create potential energy, and it's classified based on the type of force involved. An arrow in a bow, a raised stone, or a charged particle in an electric field all have potential energy, but each one has a different energy relationship. Common types of potential energy include mechanical and gravitational. Less well known are these field forces, electromagnetic, strong nuclear force, and weak nuclear forces. Let's look at types of potential energy. Mechanical potential energy. The objective of this mechanical potential energy is to restore objects to their original or natural positions. A stretched rubber band has the capacity to fling a pebble, and a stretched rubber band wants to go back to a unstretched rubber band. A bow has the capacity to fling an arrow, and the bow wants to restore the shape that it already had before. It's unstretched string. Other examples of mechanical potential energy include a taut guitar string, a yo-yo, and a compressed spring. Moving on to the next potential energy type, gravitational potential energy is generated by gravity. It's the type of energy that is stored in the stone raised above the glass sheet. And the magnitude of this energy depends on two things, two factors: the mass of the object and the height from the ground. In other words, the higher a stone is raised above a sheet of glass, the more impact it will have on the glass when it's dropped. Work is done on the glass when the stone falls on it. Potential energy from other field forces. There are three of these field forces: electromagnetic, strong nuclear, and weak nuclear forces. And these can cause potential energy too. Here's an example of electromagnetic potential energy. A magnet attracts iron because the magnet has a magnetic field, and iron in the magnetic field is attracted to it. It is drawn to the magnet. Iron in a magnetic field has electromagnetic potential energy. Now that we know what potential energy is, how do you calculate it in these problems? All types of potential energy can be calculated. The 0.4 potential energy is definable, but often it is set at ground level in gravity problems. So here is an example of a gravity problem. Imagine you're raising a stack of boxes, and the stack of boxes has a mass m kilograms and then an h, a height in meters above the ground. Newton's second law of motion states that the gravitational force on the boxes is F equals m times g. The force is equal to the mass times g, the acceleration due to gravity. Suppose the boxes fall. Gravitational force makes them fall a distance of h meters before they hit the ground. Since a force acted through a distance on the boxes, gravity did work on them. The work was stored in the boxes at height h above the ground in the form of gravitational potential energy. So we can calculate the gravitational potential energy by multiplying m, mass, times g, the acceleration due to gravity, times h, the height of the boxes above the ground. The SI unit of potential energy is joules, or capital J, which is the same as 1 kilogram meters divided by seconds squared. And actually, that is not, we'll see joules once we calculate out some example problems. All measures of energy are scalar quantities, meaning energy does not have a direction. All right. So, Dave is perched on a tree branch. Which factors determine his potential energy at this point? The potential energy depends on his mass, m, g, the acceleration due to gravity, and h, his height from the ground, mgh. Now we are moving on to kinetic energy. Potential energy deals with objects that are not always in motion. Kinetic energy is motion. A moving car has kinetic energy due to moving objects. All moving objects have kinetic energy. And that kinetic energy is determined by the mass of an object and its speed. As the speed of an object increases, its kinetic energy also increases. And a heavy object will have more kinetic energy than a lighter one if both are moving at the same speed. Think about a roller coaster in an amusement park. It's not driven by an engine. Rather, a pulley pulls the roller coaster train to a high point and then lets it go. As it moves to a lower point, its kinetic energy increases as a result of its increasing speed. As the train reaches the lowest point, it has enough kinetic energy to move up all on its own. In other words, the energy stored in the roller coaster during the downward ride is used to push it back up. An engineer can design a roller coaster track to function properly by carefully calculating the mass and speed of the train. Here are some more examples of kinetic energy. You use a hammer to drive a nail into a piece of wood. How deep the nail actually goes into the wood depends on the speed with which you strike the hammer with the nail. Because the hammer is moving, it has kinetic energy. When a baseball hits a catcher's mitt, the speed of the ball determines its impact on the catcher's hands. Because the ball is moving, it has kinetic energy. Moving objects have kinetic energy. Hydroelectric power is generated when large amounts of water fall on a turbine. The falling water causes the turbine to rotate, and that rotation generates electricity. The water is moving, falling, so it has kinetic energy. When they are at rest, they have potential energy. And when they're moving, they have kinetic energy. And that is the main difference between potential and kinetic. And the calculation of kinetic energy involves this equation. Kinetic energy, or Ke, equals 1/2 times m, the mass, times v, the velocity, squared. Kinetic energy is also measured in joules. So if you look at the units, we have kilogram times meters squared divided by seconds squared. So kilograms times meters squared divided by seconds squared. And we'll see that in the next few examples. But it's important to note that kinetic energy is directly proportional to its mass and the square of its velocity. So for example, if you double the mass, you're doubling the kinetic energy. However, if you double the velocity, you're actually quadrupling the kinetic energy because you square that 2. So if you put 2v in here and square, that equals 4. So that's 4 times the original kinetic energy. And that'll make more sense once you work some of these examples and in the mastery test as well. Consider this example. You're sitting on a fence and your friend pushes the swing to a high point, say point A, and then moves aside. This allows you to swing to and fro on your own for a while before your swing comes to a halt. You're sitting on a swing. This motion happens because when your friend pushes the swing to a high point and lets go, stored kinetic energy due to the swing's motion is used to work or to do work to take the swing to another high point. And you would use this equation to solve the kinetic energy of the swing. Let's look at the effect of mass and speed on kinetic energy more closely. A moving train with 100 cars has more mass than one with only 20 cars. The train with more cars requires more energy to stop, and both trains require more energy to stop if they sped up. Here's another example. A small snowball rolls down a hill. It hits a wooden block and stops. But a huge snowball hitting the block has more kinetic energy and maybe enough to move the block. Or suppose the hill is steeper, and so the small snowball rolls faster. Its velocity increases, so its kinetic energy also increases. The increased velocity may be enough for the small snowball to move the block as well. Fan blades are another example. They have kinetic energy when they're moving, and if you increase the mass or the velocity of the blades push more air. This has a activity simulation that you can work through, but I'll skip that for now. Kinetic energy is all around us. One good example or one illustration of kinetic energy is a swinging pendulum. Remember, a pendulum is a cord suspended from one end with a relatively heavy object on the other end. When a pendulum is at rest, it's at its lowest possible position, and that means the potential energy is defined as 0. When you push the object to one side or the other, the pendulum moves from its mean position to its highest position. When it moves, the pendulum has kinetic energy. But at that specific point where it hits the high point and starts to turn directions, the velocity is 0. It stops for a split second. At that point, its kinetic energy equals 0 because it's no longer moving at that specific second. And all of that energy is stored as potential energy. Remember, this is the highest point of the pendulum's path, so it makes sense that it has the most potential energy it can have. So at the high point, it has all potential energy, no kinetic energy. And then as it swings to the bottom point, it's moving the fastest, so it has the most kinetic energy and the least amount of potential energy. So there's a trade-off. For the highest position, gravity acting on the pendulum causes the pendulum to move back to the 0 position. As it begins to move, the potential energy of the pendulum starts to convert to kinetic energy. So all of the energy converts to one another at some point along the pendulum path. Carrie is driving a car. Which factors determine the kinetic energy of her car? Well, the equation for kinetic energy depends on mass and velocity. 1/2 m times v squared. So I'm going to stop at this point right now, and then next time we'll come back to solving potential and kinetic energy problems. Hopefully that gave you a little overview of potential energy. Potential deals with positions of objects, while kinetic energy deals with the motion, moving objects. And we'll get into more of that next time. But until then, have a great day, have a great week, and I will see you later. Bye.